How's it going, everyone? Welcome to the 8th drill of the Spring 21 semester. Today we're going to be talking about case analyses or looking for unusual data points or outliers that might be problematic, and also looking at our model assumptions. There's a library called GVLMA, which is the Global Validation of Linear Model Assumptions. I think this one might install with LM support, because LM support, some of its functions use GVLMA under the hood. I'm not 100% sure, so you might just want to double check in your packages and make sure that these are installed. And then there's this other one called Patchwork that I'm going to give you a quick demonstration of what it does. It basically is a way of putting multiple plots together in a really awesome and easy, intuitive way. And so I've already run my libraries, and I'm just going to skip down to the bottom here to talk about this patchwork real quick. And so all I'm doing is I'm making 4 plots, P1 through P4, that are just from the MT Cars data set and the Prestige data set. And I just made these 4 plots that are visually distinctive, and they're labeled, plot 1 through plot 4 up at the top. And so this is patchwork working here, where if when you have plot objects, patchwork recognizes this plus sign and slash as meaning you can think of it conceptually as beside and above. So here we have these 2 separate plot objects, P1 and P2. So P1 plus P2 gets interpreted as put plot 2 on the right side of plot 1, or if you did P2 plus P1, it would interpret that as put plot 2 on the left side of plot 1. The slash means over, so this would be like plot 1 over plot 2. Now, keep in mind, this is completely different from like using the facets that we've used before, because this is taking completely separate plot objects and kind of just gluing them together into one object. So it's not the same as faceting. But it can handle more complex things too. So if you run here where we have, well, what happens when we do P1 plus P2 slash P3? Well, it's going to take plot 2 and put it over plot 3, and then put that jointly to the right of plot 1. So it obviously evaluated it as, you can think of this chunk first, and then added on this other part. So if you wanted it to be, instead, what you wanted to do was plot 1 beside plot 2, and then both of those things over plot 3, you just use that evaluation where in parentheses you say plot 1 beside plot 2, and then you put all of that over plot 3, and that's exactly what you get. And here we have plot 1 beside plot 2 over plot 3 beside plot 4, or, if you wanted to flip that around to do plot 1 and 3 on top, whatever. So here, put plots 4 and 3 on top, and I just wanted to show you that this can be stored as, some object. So now we have this object called complex, and when we run that, it has the that plot object that we stored here. You can also, add annotations, so if you wanted to add some text annotations, that's something you can do. I think that there's a limitation that you can only go across 2 columns. Maybe there's more. I haven't needed that function, but if you really desperately need to put together a whole bunch, look into the patchwork stuff and see. And then finally, here's just, making some table in the output, but say you wanted to put this table in a plot, there's a thing for that, and you could use this text grab where now I've just pasted that table in, and so if I look at just plot 2, this is what plot 2 looks like, and then when I put that beside the table grab, it will give us that table nice and pretty next to that plot. So that's patchwork in a nutshell, and that'll come in use later because we're going to make 2 plots and put them side by side. That's why I wanted to jump off with this quick demonstration. Real quick, just here, just so that you know what I'm doing when I run this RM. This LS is all the things in a list of all the things in the environment, and RM is the function for remove, and so I'm telling it to make a list of everything in the environment and then remove it. So it clears out the environment programmatically. And then also there's this command dev off that we'll talk about more here in a little bit. But basically it's a device off, the graphics device specifically. So we some people may take for granted that, plots show up here in our studio and might think, well, of course they do. Where else will they show up? And the answer is, well, in an external window, something that's not within our studio. So there are, alternative ways of rendering graphics besides in this RStudio graphics device, which is the default. But some of the functions that we'll use later will default to popping them out in external windows in ways that are can be a pain for me. I'm trying to screen capture stuff. So anyway, we'll talk more about that when we get there. But we're gonna start with going in. We're gonna read in our prestige data, and I just want to explain through what I'm doing here, because you see that we end up with 102 observations of 9 variables. But if you just look at the prestige data, you'll see that it says that there's only 6 columns. And so one thing is that the prestige data set, unfortunately, doesn't have, it has row names instead of row numbers. So like the row names are the actual jobs that are in or the job titles, the occupations that are in this data set. But that's not a usable variable. You can't use that to label things. So first thing that we do is just pipe the data, the raw data frame into row names to column, and all that does is pulls out those these row names here and gives them the name of occupation. And so that's where our 7th column comes from. We've now created our occupation, because you remember that Tibbles, tidy data in general, does not use row names ever. Like row names are just bad. And in fact, like if you have something that does have row names, if along the process you turn it into a tibble, you will lose that information. So that's why here on the front end, I'm saving that information into the data frame. And then finally, I'm just going to go ahead and put the horse before the cart and mean center both the women and education variables. So as a reminder, the things that are in this data set, we're looking at different occupations from like the 70s in a Canadian census. I'm pretty sure it was Canadian census. And the variables are the years of education of any particular job, the average income, the percentage of women in that field, or that percentage of that field that are women, the perceived prestige that, how the population at large rates the prestige of these various things, some census code, whether it's professional, blue collar, or white collar, and then now my centered variables, which will briefly take a look at and reinforce why we centered those when we get to the models. So we'll just jump right in and say that we want to see if we can, if the income one earns is predicted by the percentage of the field who are women and the years of education. And we're going to go ahead and use the centered predictors. And so, simple enough, regress income on centered women and centered education from the DF data frame, and we're going to create the model. So the first thing that we're going to do is we're going to conduct case analyses to look for problematic cases. All of these functions are going to be from the LM support package, and we're going to be using the model case analysis function, and then you can tell it what type of analysis you're wanting to do, which is you can enter in residuals, univariate, hat values, Cook's D, DF beta's influence plot, or Cove ratio. We're not going to talk about all of these things. If you want to dig into it more, you can. We're just going to hit the highlights on the most important ones, or at least the most important ones for what we're doing. And so what we're doing is we're looking for cases that are clearly problematic. That the thing that you really need to keep in mind when you're doing these, and this is probably the question that I get most of previous students coming through and saying like, "Hey, Austin, I'm working on X, Y, and Z, and can you double check this for me?" It's usually either power analyses or these, model assumptions and case analyses, and people just trying to figure out whether or not, the assumptions are met and whether or not, people need to be removed from the data. But there's no hard and fast rules for any of this. What I tell people, and the way that I personally do it, is when I pre-register my studies, I say, like, I'm going to, model case analyses will be conducted, including looking at studentized residuals, leverage Cook-Stee, and problematic cases will be flagged. And, when cases are problematic across several metrics, when there's converging evidence that, like, yes, this is problematic in either severely problematic or problematic in multiple ways, then it will be considered for removal. But any removals will be made explicitly, and I justify in my it's not the kind of thing that I hide on the back end. Like, I say clearly, like, I removed 5 participants from my data for these reasons, and then also I make the analyses with the people still in it available in supplementary material. So I still I still want to check and make sure that we're taking out these 5 people doesn't fundamentally change my conclusions, but it should give us a more accurate model. So just keep in mind when we're going through this, again, that you're not just looking for oh, this one looks like it's significantly outlying in the residuals, so that means we remove it. No, that's not what we're doing ever. It's kind of a holistic look at, okay, are these in general problematic? Not does this meet some arbitrary cutoff? If so, then take them out. So just keep that in mind as we go through this. So the first thing that we'll do is we'll look at the studentized residuals. And so with the model case analysis function, we're going to put in the model, and then we will tell it residuals. And when I run this, I have this note here to notice the stop and finish buttons. And what I mean is, right here, you'll notice that in your console, this is running still, and it doesn't stop. And then up here in your plots, there's this finish button, and it says this locator active. And what that's talking about is here is this plot that we've made of the studentized residuals from this function. But this function can actually do a little bit more, because you can mark things. So whenever I click here over on the plot, if I click way off away, you'll see down here where it says that no point within 0.25 inches. And what it's saying is hey, you're trying to identify a point by clicking on it, but we're not seeing one. But if I click down here, you'll notice that I don't get that warning. And then I'll also click on this one over here, because basically these two are beyond this red cutoff for our Bonferroni corrected 0.05 for outlying studentized residuals. So the reason that this is still running, and you have to click this finish after you click on the points that you want to identify. And now when I click finish, it will tell me the row names of 2 and 24. And this one is whatever is row 24, and this one is row 2. So then, if we want to see what those 2 rows are in particular, slice is the dplyr function that chooses things based on its location. And so if you just tell it slice and then give it combined 2, 24, then it knows I want to slice this data set, and I want to pull out just rows 2 and 24, which we can see row 24 is physicians. And then this row 2 is general manager. So these are the 2 occupations that seem to have significantly outlying studentized residuals. So, and if you're wanting to look at this in base R, the same thing, but using the bracket notation, you just within the bracket say from the data frame subset rows 2 and 24, comma, and leave after the comma blank, meaning all the columns. And you basically get the same thing. I strongly advocate for keeping everything tidyverse, because it's the kind of thing that, this versus this might not make a difference now, but as you get into more complicated things down the road, this is scalable and expandable. This becomes very difficult. Anyway, so looking at our residuals there, there's a couple cases that, all right, these two look like they're potentially problematic. And really, studentized residuals is probably where I put most of my emphasis on case analyses personally, because your residuals is really where you're talking about, are the data fitting with the model well or not. Some of these other things, for instance, now moving into our leverage or the hat values, here you can have something, leverage is where it says that leverage is a function of extreme values on the predictor variables. One way to think about this is that leverage is an unusual combination of predictors. And so you can have something that's an unusual combination of predictors, but it's still the error from whatever its predicted outcome is, it is still small enough that it can have a large hat value, but still be well fit within the model. So it could still be one of these down here, even if it does have high leverage. Or you can have something that doesn't fit well in the model, but has low leverage. And so if we look at our model case analysis and put in our hat values, again, here we have the same thing. We have our stop sign and our finish button up here. And so there's only one value that is above the cutoff for, the red. And that one is row 84. And so when we slice the data frame to get 84, we get that that is our sewing machine operators. Now, I want to jump into another quick. I'm going to skip down to the bottom because I want to make a 3D graph to try to kind of demonstrate what it means to be kind of like an unusual combination of predictors, but one that doesn't necessarily mess up your model. So down here, I'm just going to run a few lines that you don't need to really worry about. Point is just to get to the actual plot itself. And when we get to this plot now, we have this 3D plot that instead of, we've all semester we've been making scatter plots with regression lines. Well, that's essentially what this is here's our scatter plot and this is our regression line, only since now we're actually on 3 variables, it's not a regression line, it's a regression plane. So we have, women over here, education over here, and income on our z-axis. So that colored thing is basically what our model is predicting. You can give it any particular value of centered women and centered education, and it will give you what that predicted value is. And you can see that in general, a lot of these points are right around that. There are some up here that are really high. We've got our physicians and general managers, for instance. They're making substantially more than a lot of people. But the one that I really want to focus on is down in here. It's right here is our sewing machine operators. So you notice that it's pretty far off that predicted thing, because it's a weird combination. It's because it is a field that is mostly women. If you just look in terms of, it's at the max of the women, and also down here for education, it requires almost no education, but they actually make pretty good money. So for given this model, you wouldn't really expect there to be such a high percentage of women and, such a low education thing. That's an unusual, it doesn't really fit well with the other cluster of data. So that's kind of what we're talking about when we say that it's kind of an unusual combination of predictors. It's just, it doesn't really hang with the others. But importantly, that one point, so that's why it has a high hat value, it has high leverage, because it's this weird you know, uh, a weird combination of on the predictor variables, but importantly, like it's not a heavy enough value that it's like pulling this regression plane up. It's not impacting the model. It's not a matter of the like the rest of these points not fitting well because this one point is pulling this corner up in a way that makes that entire plane, not fit well. So, so that's kind of what this is talking about. This one has high hat value because it's this weird combination of predictors that you don't really see in any of the other things. No matter which angle you look at this from, it is alone in space, essentially, in 3D space, or I guess in two-dimensional space since we have two predictors. But you get the point. So moving on from there then, so we have our sewing machine operators that have high hat values, and general managers and physicians have, potentially problematic residuals. So then if we look at Cook's D, this is how much the model parameters change when you exclude any given case from the data. And so here again, this will give you the two cutoffs for high and low. Because there is no green line, what that means is that like the green line is pretty far above, because it's up here at 0.5, and Bill recommended around 200. In previous iterations of this course, I had gone with 100 as my cutoff. But if Bill is saying 200, then I'd suggest 200. But anyway, point is, I just wanted to show you that if I go through and click on all of these points, regardless, and then click finish, it will tell us 2, 17, 20, 24, 26, and 84. And so like if you were wanting to look at all of those different things, if like let's just say we were going to go with that red as our cutoff line and wanted to inspect, well, which of these things are above that red cutoff line, just click on them and then click finish, and it will tell you which ones you clicked on. If we look at that again, and then like just say like, well, let's look at these two that are way out there. Like these are past this cutoff, but like these two are pretty clearly in separate clusters as far as Cook's D. And unsurprisingly, it is 2 and 24, which we've already seen is our general managers and physicians. And so then finally there we have our we'll do an influence plot, which is one plot that shows all of these things. So when we run our influence plot, what we see here is we have our studentized residuals on our y-axis, our hat values on our x-axis, and the size of the circle is scaled to Cook's D. So once again here you can see we've got our stop sign and our finish because it's wanting us to click on things. So let's click on stuff that's that looks strange. So we've got this one up here that's just way out to the side. We've got this huge one up here that's residuals are way far off, and this one over here. And so if we click finish, we'll see that that's 2, 24, and 84. So again, this 2 and 24 are our general managers and physicians, and then this one over here is our sewing machine operators. So sewing machine operators and physicians influence the model a lot, because it's this Cook's distance is way far off. That those pull those estimates quite a bit. The sewing machine operators, its leverage is high, but its Cook's D isn't like terribly concerning, and most importantly, maybe not most important to me, most importantly, its residuals aren't that bad, so it's not like messing up the predictions in the model, and so that one's not terribly concerning. So when you kind of put all this together, we've gone through and examined the impact of each of these cases on the model, and it's pretty clear that general physicians general managers and physicians, are potentially problematic in the model. Um, the sewing machine operators, although their leverage is high, it's well fit. Its residuals aren't worrisomely off. And so what do we do with it? Well, the first thing that we're going to do is, you would want to go back and check your data for errors, make sure that there wasn't any things. In this particular data set, that's not a problem. It seems unlikely in this particular case that it's a data issue. The second thing is to stop and ask yourself if there's any reason that, these potentially problematic cases, some sort of systematic reason that might explain why these aren't fitting in the data well and why they seem unusual. And it's possible that, if you could think of some other variable that, like, oh, well, this and this are related to this other variable, and so if we account for that as a covariate in the model, then that helps alleviate these problems. And so there could be like a third variable problem, some hidden variable. That notwithstanding, if finally, a third step would be to look at the impact of just removing those cases from the model. And so what I'm doing here is I'm pulling just the coefficients table of the summary from the model. And then here I'm doing the exact same thing, only I'm adding in a filter. So I'm taking the data frame, piping it through a filter, and note the exclamation point here. So I'm saying not occupation in general managers and physicians. And so, if you're familiar with like this percent in percent, I'm pretty sure I've used it before. That looks for something in a list of something else. By putting this negation, this exclamation point in the front, it's telling me to filter things that are not in this list of things. So all that's doing, in short, is filtering out. And so instead of 102 cases, it would only be 100 cases, because we're taking out the row of general managers and the row with physicians. We're piping that into the exact same model, piping that into summary, and then that coefficients table. So in short, this is literally the same as this plus what we ran at the top, except for we're taking out those two cases. So that said, if we look at our original summary and now our new summary, what we can see is that it shifts our estimates a little, but importantly, notice the standard error of this filtered model. We've taken out those two problematic cases, and it's reduced our standard error across our things quite a bit. It's also changed our estimates a little bit, because before the general managers and the physicians had very large incomes, and so the overall average for average percentage of women in average education with general managers and physicians in the model. The average expected income for someone with average, or the average percentage of women and the average education, would be $6,797 a year. $6,800. Once you take out those two particular cases that have, unusually high incomes, that estimate drops, a few $100s down to about $6,500. And then for each 1% above the average of women in the field, before, it was expected to decrease that income by about $65. That slope's gone down a little bit. Now it only is expected to decrease by, $57. But importantly, the patterns and directions are the same. So there is still this, these effects of both women and education. It's just reduced that standard error and given us a little bit more accurate estimations of those parameters. So Then here, just real quickly, I just wanted to reinforce why we use the centered predictors. So doing the same thing, but using those raw predictors, where if I wouldn't have centered the variables here, instead of talking about, the predicted income would be 6,500 for, average percentage of women and average education, I would instead be saying, the predicted income for an occupation that has 0% women and 0 education is expected to be negative $571. So, centering that again, I just remember that doesn't affect your slopes here. The slope of women and education are the same. All that does is affect your intercept to give you a more interpretable intercept. So removing these two cases decreases those standard errors, but everything still, the patterns are still there, the significance is there. So in this case, either decision could be justifiable. This says that, fortunately, that it's not particularly consequential, because either way we run this, we still come to the same conclusion. That's not always the case. So that you may run into a case one day where, you run a model and you get super excited because your results are, what you expected. But then once you look at this, you realize like, oh, wait, there are some outliers, some problematic cases. And when I take these problematic cases out, my effects go away. Like I no longer found, like it does change my my conclusions. And when that's the case, it's unfortunate, but like you really just have to make your case one way or the other. If you do decide to leave out cases, you should always report it in your write-up, that you excluded cases and what they were in particular. I always also include them in supplemental materials that I make available when I submit my articles. And like for this particular model, like the best way to actually handle this data would be to do some transformations, but that's a different drill. So for now, we're just going to go ahead and refit the model as that filtered, when we're going to take out general managers and physicians and refit that model. And so now we have our model, and we want to inspect our model assumptions. And before we go on there, one thing that I want to point out is that here, now that we refit our model, you don't want to go back through now and redo your case analyses again. Because if you do, like if we rerun these case analyses with this new model with these two particular points filtered out, things that before were not problematic might then be problematic. But basically, like as you're trimming out, essentially you don't want to keep checking for outliers, cut off one, and then recheck and say, all right, well now is something that was a lower value an outlier. Like this is like a one-stop deal. And any of the problematic things you want to do with all of your data, and you don't want to just keep whittling down until, oh, well now when I run the model through, none of the cases are, because like I said, you'll continuously keep trimming off some of these values, but it's with incomplete information, and so it wouldn't be appropriate to continuously keep running through these and trimming off as you go. Like that's where you start getting into questionable statistical practice territory. Anyway, so with our model assumptions, the general linear model makes 5 primary assumptions about the structure of the data. 1, that there's no measurement error. 2, that there's independence of residuals. 3, that there's normality of your residuals. 4, that there's constant variance or homoscedasticity. And then 5, the linearity of the relationships. Now, having violations in these assumptions are going to have it says inefficient standard errors, and that's here. Where if your standard errors are increased, it's going to decrease your t-value and make it harder to reject the null. It's also going to give you inaccurate parameter estimates. assumption one is always violated to some extent because we can't measure things perfectly, but I mean, it's kind of an accepted thing that we have to like start with the premise of like, okay, assuming that like there's as little error as possible. Assumption two is one that we're also not really concerned with because it's usually if all the other assumptions check out, this one is usually not a problem, and that there is like a way to test, finger quote test the independence of the residuals, but even that has problems, and so we don't really have to worry about it. Like number two is in particular is usually a design issue, not a data issue. If you have randomly assigned conditions, for instance, like that is they're going to be independent. Like that's why we do the random assignment, and so that's usually a design problem if you have dependence in your data. If you're taking multiple measurements, now you have 2 observations, 3 observations, 4 observations per participant. There's dependency in your data, and so you can't do a general linear model with that. It violates that assumption of independence. If you have dependence in your data, one solution is something like multi-level modeling, the mixed effects models that we very, very lightly touched on in the context of repeated measures specifically. But that's a whole other course, so we're not going to get into it. But assumptions 3 through 5 is what we can test and look at with LM support, and that's what we're going to do. We're going to look at our normality, linearity, and homoscedasticity. So when we look at the normality, it's important to remember this is like the number one thing that I hear people messing up is when they want to look at something and say like, oh, well, I looked at my distribution of women in the field. So let's, in fact, say if we look at performance analytics chart correlation, if we look at our univariate, by the way, I'm pretty sure, again, I've shown you chart correlation before, but just another shout out to it. It's a pretty awesome function that it gives us our correlations on these diagonal, or on this corners, and the bivariate plots, scatter plots here on these side, on this side, and then our univariate distribution on the diagonal. And so like you might look at this and say, well, hang on, like income is not, like this is not a normal distribution, like that's a problem. Well, no, it's not, because that's just the univariate distribution of one particular thing. The normality that we care about is the normality of the error of the residuals. So after you put all of this stuff in together, because while this might not look normal, once you use that in combination with other predictors, like it might still be able to make, fine predictions. Like it depends on a whole bunch of other stuff. So what I'm trying to drive home here is don't look at this and say, oh my God, my income variable or my women variable, like this is not normally distributed. Like I'm violating my assumptions. Like, no, you don't know until you look at the residuals of your model, whether your model is violating its assumptions. So one way to look at this is a QQ plot. And so all this is doing is I am creating a data frame here called dists, and I have 4 different distributions: a Cauchy distribution, a normal distribution, a uniform distribution, and a beta distribution. And I'm just randomly drawing 100 values for each distribution. This set seed is just to make sure that when you run the script, like you'll get these exact same 100 values. And so now I've just created this dists, thing that just drew 100 random numbers. And so now I'm going to take those and I'm going to make a couple plots with them, and then put these plots side by side. This is where that patchwork comes in, that like if I look at just D plot, it's just the density plot, and then Q plot is that QQ plot, And so then we put them side by side, we can look, given, this distribution, here's what a QQ plot looks like for it. So you don't really need to know anything about these distributions besides, this is what that distribution looks like, and this is the exact same data on this QQ plot. So what you're looking at for on these QQ plots is, you basically want all your dots to fall like on this diagonal. And so it should fall along this line. You don't really want to see like tails flipping up substantially, or making big S curves or anything like that. You'll occasionally have data points, and this is really important to consider that this is a normal distribution. Like this is a random sample of a normal distribution, and so real data is never like the perfect, pretty bell curve. It's going to occasionally have a little bit of a not perfect shape, but that doesn't mean that it wasn't drawn from a normal distribution. The exact same thing applies to your data. So just because some variable that you measure on participants, like you expect in the population it to come from a normal distribution, just because when you draw it in your sample, it's not the perfect bell curve shape, that doesn't mean that it's not normal. More to the point, when you look at your QQ plots, when you have like these couple points that are like a little further out, or like they kind of deviate away from that line a little bit, that doesn't mean that you just have to throw it all out and it's pointless, or be like, oh well, that's an outlier and I need to cut it off. Like, no, that's you should have outliers occasionally. I mean, if you think about it, like it's just because it's less likely doesn't mean it's impossible. And so, you shouldn't necessarily just throw somebody out because they are particularly high or particularly low. That goes back into the case analyses that we already did. So point is that, like, when you look across these distributions, you can see that, like, this QQ plot is how we can see, look for the normality. And so we can see that, like, nope, this distribution is pretty clearly not falling like on that diagonal line. And this one also, like, our line is not diagonal. It's this flat thing and has this weird curve and this one pop way up here. This normal distribution, surprise, surprise, it does. The QQ plot, like, it falls, more or less along that line. And then this uniform distribution, it curves off at both ends. Here in the middle, like, it kind of kind of looks like a normal distribution if you look here in the middle of the data, but here at the ends, not so much. Point is, when you're looking across these QQ plots, this is what you're really looking for, is that those points fall on the diagonals, and the tails aren't like jumping out, essentially. So again, going to be using this dev off thing, because as we get into now we're going to get into the model assumptions function. So this is different from model case analyses. Now we're talking model assumptions. At least when you're in Mac, it will open up a graphics device that's called Quartz. I don't know off the top of my head what it's called in Windows. And so the behavior, if you're on a Windows computer, may be a little bit different than what I'm dealing with here. But ultimately, it's not a problem when things pop up in external windows. It's kind of a pain for me because I'm dealing with trying to, capture my screen, and so having multiple windows popping up and not just having things over here. So that's why I do this. So I'll use dev off to clear out my plots in between. Point is, model assumptions will give you these QQ plots and a lot more. Now here I talk about, it will also spit out, significance test, and I finger quote significance here, because again, like, these tests are not substitutes for visually inspecting your residuals and like looking at these plots and determining whether things look problematic. So I'm going to put it on our model, and for model assumptions, I'm going to, and then we'll be looking for normal. And sorry. I just remembered this, unfortunately, is one of those things that so I'm just going to create a subset of this data because I'm kind of doing this here on the fly. And the problem, the LM support doesn't necessarily want to work nicely with tidyverse. So whenever I put that in, what this was telling me, and you may run into this problem on things as well. It was telling me object dot not found because under the hood, LM support can't necessarily interpret the this pipe code and the way that tidyverse reads it. Where in the model itself, I actually had the period, that placeholder for the pipe, coming in as the data frame. And so all I've done now, and come down here, and obviously this will be here on the script when you see it, but I'm recreating that model just using a data frame that's separately subset, and then putting in, you know, this second data frame that I've filtered out these couple things. So sorry about that, but now when we look at our model assumptions, you know, it's going to spit out these you know, statistics for us. And so we look over here at our QQ plot and our normality plot. So this is the GVLMA output. And according to this, like, the skewness is acceptable, but like these other problems, you know, it says are, you know, not satisfied. So the global just being kind of like overall, are the assumptions met? And then kurtosis being, you know, how peaky it is, tall and peaky or flat and wide. Skewness being, you know, pushed off to one side or the other. You know, link function you don't need to worry about. And then heteroscedasticity, like that's something that we do have to worry about. But this says that, you know, these are all not satisfied. But again, like, you can't take this as the biblical truth. Like, you still have to look at these things, because the problem is that as your data set, these p-values, the tests that these p-values are tied to, are not asking a question, is the heteroscedasticity, you know, problematic? Or, you know, is the heteroscedasticity, you know, close to zero? It's testing, is it exactly zero? Like, exactly perfectly zero. And as you have more data and your standard error gets low, literally anything that is not exactly zero will have a p-value of less than 0.05. So my point is that, like, especially, you know, if you happen to take multivariate, or like when you start dealing with bigger data sets, if you have 3,000 observations in your data, you can, if something that looks just about like a perfect bell curve, you know, this might tell you is significantly skewed, because, like, yes, it's not, the skewness is not perfectly zero, and with 3,000 data points, you can say with a lot of certainty that the skewness is not exactly zero. So, you know, these all go down as your sample size goes up. And that's why, like, we're telling you, don't only look at, you know, this and say, like, nope, it's no good. Instead, like, you still need to actually look at these plots and think through these things, and then make the call about whether or not assumptions are violated. In this case, though, when we look at it, like, yeah, like, this is not, like, this doesn't look good. You know, again, we'd want our dots to fall basically along this line here, but you can see this dotted, these dotted lines. That's like a lowest band, which means that like kind of if you take this in chunks and like analyze like, you know, where's our predictions for like this range, and then separately for this range, then separately for this range. And so if you kind of make adjustments as you go, where are they? And what this is telling you is that like, no, that pretty substantially, this tail end pulls down, this one jumps up pretty high. Like that's really not a great looking QQ plot. Like this is potentially problematic. And then again here, like, you know, if this blue dotted line is a normal curve, and the black line is our studentized residuals, like that's pretty clearly not a normal distribution. So, you know, our stuff with our QQ plot, our residuals are not looking great here. But, you know, it's not quite time to just throw out the baby with the bathwater and call it quits. You know, there's some problems with normality, but like we don't have to jump to any conclusions just yet. Like you know, we can do things to salvage it. So the next assumption is constant variance, and so basically all this tells us is that you know, given some predictor, if you look at your error, you know, along some x-axis, you know, you shouldn't have like just a little bit of error in the middle where it's like pretty tight predictions, but like down at the ends, you know, you have the big bow tie shape, or, you know, a football shape where at the ends you can make, you know, predictions that are pretty close, that the residuals are small, but, you know, once you get into the middle of the data, the predictions are kind of all over the place. So what we're going to do is we're going to plot our predicted values against the observed values by telling model assumptions we want constant. And so that's what we're doing here. And what you can see here, you know, you could almost think about this as like a sideways cone, or like a triangle kind of thing. And so if our fitted values are here, but our errors are on the y-axis, you can see like here, all through here, we have a pretty consistent, you know, kind of scattered grouping of error. But as you move this way, that error gets a lot more. So down here at this end, we aren't making as good of predictions as we are here in the middle or down at this end. It changes. We don't have consistent variance. The variance increases as these values increase. So here what you'd want to see is this pink line more or less fall along that blue line, but that's not what we see, because down on this end, like we have like no residuals that under predict. Well, I guess that's because they're absolute, obviously. But point being that, you know, again, basically you can see that, you know, here as we move down, it's that variance gets more and more drastic. So again, that doesn't look great. Like this is not what I would want to see if this was like my data in this model. But once again, like fret not, there is still things that we can and ultimately will do. So the final thing that we're going to look at is the linearity of the residuals. So if we run linear as what we're looking for in the model, and you'll notice down here it says hit return to see next plot. So like click down here in your console and then hit enter. And now it will pull up with your component and residuals plots. So if you imagine that here with this lowest line, like imagine if you took, let's just say, for example, education values of 6 through 8 and plotted a regression line and put it in pink. And then, you know, just looked at 8 to 10 and plotted a regression line, and then 10 to 12 and plotted a regression line. That's what a lowest is, this pink line. It is a localized fit. And so if you have linearity of these predictors, then it doesn't matter. Like your slope should be about the same between 6 and 8 as it should be between 12 and 14. And that should be the same as between, you know, 10 and 12. Anywhere along this line, these localized, you know, slopes should roughly fit. And, here is like that's basically what we're seeing. So as far as linearity, we're good here. There doesn't seem to be any systematic shifting in the residuals as you slide up or down women, the value percentage of women in the field, or the years of education. So this assumption at least looks like it's in pretty good shape, that we do seem to have our linearity. So in short, this data does in fact seem to violate our assumptions. We don't have normally distributed residuals, and we don't have constant variance. We do at least have that linearity. And so it wouldn't really be appropriate to try to draw inferences from this particular model. It violates the assumptions of the modeling approach that we're taking. But there are ways that you could transform this data that would solve some of these assumptions. And so that's what we'll be getting into later on. That wraps up what we had to cover for today. As always, if you have any questions, feel free to let me know. And I will see some of you on Tuesday.